adjust the date, so I will. Yes.
Somebody is the recording.
It's recorded.
Okay, welcome everybody to the colloquium today, HO colloquium today by Alina Donia. It is my great pleasure to introduce Alina. Alina Donia is a senior lecturer in astrophysics and applied mathematics at Monash University and a PhD supervisor in solar physics, a coordinator of a machine learning data application group in solar physics, BSc and Diploma Physics from Bucharest University, PhD Mathematics and Astronomy from Romanian Academy and Max Planck, Graduate Certificate, Higher Education, Monash. She teaches mathematical modeling and advanced engineering mathematics as well as astrophysics and visualization in mathematics in the School of Mathematics. Her research field is focused on helioseismology, wave mechanics, acoustics of solar spots, magnetic fields, solar quakes, and solar flares. Expert in helioseismic holography, a mathematical method which can tell you how loud is the sun, Alina can detect solar quakes in satellite images from state-of-the-art instruments. Her recent interest is in acoustic detection of flux emergences, sunspot stability, solar quakes, and applying deep learning AI algorithms for solar imaging and space weather forecasting. Dr. Alina Donia also serves as the founder and academic leader of MHAB, Monash High Altitude Balloon, guiding a multidisciplinary team of students across engineering, science, IT, and business in developing Australian research-driven stratospheric balloon missions. Today, Alina will be speaking on acoustic reservoirs beneath and around sunspots, clues to sunspot stability. To Alina.
Okay, thank you. Thank you for having me here. I can't wait. Last time I was here as a staff member was in 2014 when I had my sabbatical, and Laura was just that size. And now I think I know a bit more about sunspots than I knew at that time. And I'll dare to pose some questions here for you so that we can hopefully collaborate together and I can learn about the reservoirs that all this acoustic emission that happens around sunspots. So the key point here is to understand the structure of sunspots, and if we can see if we can say something about the stability of sunspots. Beautiful image of a sunspot stolen from the internet. So with helioseismic holography and with helioseismic measurements, most of the time we try to assess regions, magnetic regions that absorb acoustic waves. It can be a plage, it can be a small pore, it can be a small sunspot, it can be a big active region, and so on. So what I like to show this movie because it has everything in it. We have the Solar Dynamic Observatory images, we have the HMI instrument, right, the magnetic on the right, image intensity continuum on the left. Then you would follow a tiny active region, a sunspot. I don't know, a pore, something very small, frankly, that I wanted to observe. And I wanted to ask, what's the acoustic map at 3 millihertz of that signature as it travels across the disk, right? So you could see it in a 3 millihertz as an acoustic power map, just here, this tiny thing. Of course, the big signature that you see here, it's absorption from the magnetic plages, this positive polarity that is just trailing the big active region. So we know this, right? This kind of mapping is very familiar for helioseismologists, and we can interpret this. Interestingly, at the same time, on the southern hemisphere, we had another tiny sunspot emerging, and we could follow the same structure here of the acoustic power to see how it evolves. Because with this understanding the stability of sunspots, hopefully will send me very soon into understanding emergencies of flux emergencies, because I'm really interested in going into this field. Not necessarily just sunquakes, right? I'm moving away. I want to learn about this. So that's standard mapping for us to understand what happens here with a spot emergence or something very small. You see, in the magnetic maps, my mouse, I don't know where is it. In the magnetic maps from the left to the right, we see that growth with a polarity, positive and negative polarity, and then the acoustic local maps follow this. So why I'm showing you this is because I want to say that seismology is very sensitive at any kind of magnetic field structure at the photospheric level. Be it small, as those dots where we see it's just plages or some reminiscent magnetic field, or a big sunspot. And of course, I want to go to big spots first to understand their stability, because this is the most interesting thing when you see a big spot and you follow it on the disk and then it's returning back on after another week and it's like it's here again, and why is this? And it's even better if far-side helioseismology can spot that big spot. So this is a list. It's not updated to this cycle, but this is a list of the biggest active regions on the sun, and their units are in these mega hemispheres. And the one I'm going to focus today is, I keep going up, 2192, which is one of the biggest one. And what's interesting about sunspots is that they are stable, of course. They are complex in terms of magnetic field. We want to know if they flare. We want to know if they couple with other sunspots, as we've seen from Matthias' last talk. But also we want to see if during their evolution, if they keep their own structure or they dynamically reshape, split, because we have these light bridges run across big sunspots. And that graph in the middle shows the size of sunspots versus time. And as you can see, some of them, the 12192, I don't know where's my mouse, but the green one, the dashed green one is 2192, the one that I'm going to analyze now. So I'm learning about evolution, size of how people classify sunspots, because one day I'll say something about star spots. So you see, I'm very ambitious. People from stars, they are interested in this stuff. Okay, so so these are my questions. And I want to understand what means the equilibrium configuration of a sunspot. And we know that this is determined by the balance of forces due to gravity, magnetic field, and gas pressure. The external pressure versus what's inside, standard, equilibrium here, we have magnetic field inside. I've learned that the geometric keys, the key geometric facts here to destabilize a sunspot are related to the fact that the magnetic field fans out near the surface, right? We have keywords like curvature and magnetic tension. And then the boundary of the flux tube is concave towards the external gas. And there are instabilities here. And this geometry seems to actually raise immediately a red flag in terms of, is this sunspot from the MHD point stable or not? On the right side, it's a model of a magnetic depression of any kind of observed sunspot. And we have here the inner and the outer contours that represents umbral and penumbral boundaries. I'm highlighting this because what I'm going to show you happens mainly around between the umbral and penumbral boundaries. And I wanted to learn more about this. So this was a good sketch to show me what happens in sunspot. Then I'm going straight to monolithic and models of sunspots. Massive sunspots surely should have a very strong solid monolithic configuration that lasts with probably the least perturbation, depends on the environment and internal instabilities. But Parker said that to have this long-term stable sunspot, the magnetic structure of a sunspot has to be represented, and that's the image that I would like to. I'm going to have a poster in my room of this one. I think it's very important for what I want to tell you. So these clusters of magnetic flux tubes that hold together and converge are there because they have this converging downdrafts, they call it, below the surface. So the question is, has anyone verified this? How can we do that? So then I slow down a bit and say something about stability depends on, again, these two competing influences. What is this stabilizing the sunspot, and what's stabilizing? Stabilization means looking at the external vertical pressure gradient, right? We know density stratification and maybe gravity works here. While from inside, my focus is on magnetic tension that tries to rearrange the flux. And it's not just nice pictures with me understanding stabilization of sunspots. It's also a lot of mathematics and those equations. An extra bit for those who are not familiar with helioseismic waves is that to understand stability of sunspots, we decided to look at frequencies around 3.5 millihertz, where the oscillation power is the highest one. And these would be the waves that reflect back into the solar surface. They are evanescent waves. And this graph here, I don't know, where's my mouse? The graph, so the top graph is at 5 millihertz waves that they keep traveling into the atmosphere. And the three bottom waves show they are evanescent waves that are trapped inside the sun. So we are looking at acoustic waves at 3.5 millihertz that are trapped inside the sun. So we want these images to tell us something about the stability of the sunspot. The technique I'm using is called computational acoustic holography. You might have heard about this, where we collect the signal psi into an annulus. We call it a pupil. It's a lot of geometry here with the green functions. The idea is to find out what waves are converging from one, let's say, source or one point on the solar surface. How do they converge? They can get out, and how we can then collect them somewhere in the pupil and then return them back in time into where they came from. So this back and forth mathematical calculation here is called acoustic holography, and we use the power of all these terminologies here. It's called power, what do you call it? Acoustic power holography, to assess maps for our understanding of sunspots. So this is the paper that we got last year published. We had back and forth with the referee, back and forth. It was never ending. I was praying that one. Finally, we ended up with submitting something like 27 pages for the referee in the end to just convince that this is a real signal. So it was very satisfying in the end that we went through this. So what happens here? That's the sunspot. It's one of the largest sunspots. You see the size of it. Most of the sunspots are giant sunspots are up to 50 megameters, I think. The rest are small. We have the magnetic map, HMI data, and this is the map, the phase shift map, calculated at between, let's say, the frequency band between 2.5 and 4.5 millihertz frequency, with a focal plane on the surface. So this is terminology for the holography to tell us exactly what is the technique to give us that map. And then then we start comparing what do we see on that one. So we have a phase shift, and it's in radians, and there are some bright pixels, but the dark pixels show us this negative phase shift. And we call these strong acoustic scatterers. And they are everywhere, good news. And they are true. We cleaned up the data. We applied even shower glass effects to clean the data, everything. These are there. But that map, because the signal to noise is so hard to get, to show us information, this map is integrated over 24 hours. So it shows structure. It shows that there are some interesting acoustic scatterers at different locations. Most of them, and again, I don't know where is my mouse, most of them are around the Umbra Penumbra. Nope. Umbra Penumbra edge. And we have a big one at the top there, and we still try to understand what is that. So the mapping, if we want to, identify now the acoustic scatterers and assess properties of these, looks like that. So we have a few of them. The red one are the strongest one. The yellow one are less, let's say, less strong. But then we have a bit of a plateau where there is right in the middle where we don't know exactly what is that, because there is no bridge associated with the dark, what's that, dark blue scatter. That's the resolution as we have it. It's about 6.5 megameters per acoustic scatter. If in reality what we see is smaller, then we'll be even happier to understand what are these and how they connect with the magnetic configuration. This is a time when we want to bring more multi-wavelength analysis to assess what are they, right? Then we asked if these strong acoustic scatterers are submerged structures beneath the photosphere. So we changed the focal plan in holography to went down, and we could see that some of these scatterers, ABC, as we go down, they become weaker and weaker and weaker. So that tells us that this is actually a photospheric surface effect. So these are seen to quickly fade in the submerged focal planes.
So what are you plotting there?
It's a profile of the emission. You see that segment A, which is it's a tiny segment just across the acoustic scatterer.
Okay.
It's a profile of the phase shift to understand what its shape and if it's circular, if it's has anisotropy inside. And we plot it so green is the scatter, the signature of the scatter in that profile of the line at solar surface. And then we have a depth of 1.4, 2.8, and 4.2. No, it's the opposite. The opposite. 0 is the, yeah. That's what I said. Okay, this shows a deep signature, right? It's the big face. So this shows that it's a surface effect. And then this green thing is at 4.2 megameters down, which means that there is nothing there. Yeah, the opposite.
Thank you.
So they are really conspicuous, sorry, and visible. And we've done a lot of statistics to understand what's the, what are the errors here and what is the 1 sigma realization noise into this. The question, what are they, right? More statistics. I don't want to get into this. So this is it. This is the slide that I would like to highlight. So we have the Parker models with the magnetic field lines panning out. And we have the suggestion from Parker that we have these bundles of magnetic field that cluster as we see in the sketch. And we believe that the acoustic scatters that we see are a representation of scattering of waves going into the sunspot and being scattered away from different locations. Now, if the acoustic scatterer is one of these in between the bundles, let's call this a pocket of gas, right? So we define this as pockets of gas, and this is the bundle. If the acoustic scatterer, so the blue line going in, the waves, acoustic, they scatter on the magnetic structure or on the hot piece of a pocket of gas, it's something that we don't know yet. I would like to highlight here is that helioseismic maps show these apparent structures of Parker fragmentation of magnetic flux beneath sunspots. And I'm happy with this. And then the pockets of hot gas become trapped in these gaps between the magnetic strands, right beneath this. And they have a role here. They have to cool the monolith, the overlying magnetic monolith. And Parker's model, and I've written here this, shows that this configuration is thermally susceptible to rapidly growing overstable oscillations. So what does it mean? Holography can detect the scattering effect, but we don't know actually if the overstable oscillations that are generated under this model can be detected. We can't. So holography can't detect this rapidly growing overstable oscillations. We know that these pockets of hot gas or the bundles of magnetic field can excite waves because of this overstable oscillation happening inside the bundles. So these excited waves can carry energy downwards, because with holography, with seismology, we can't see any of the waves going up. And definitely that means cooling of the subphotosphere, of the shallow sunspot subphotosphere. And maybe you would like to visualize this with these cones where they are pushed together by the downflows and the pressure, external pressure. And you could see that the Parker's model may be visualized if we see with these cones. And holography cannot see the scatterers at lower depth, because you see how the magnetic structures are becoming thinner according to his model. So we don't have that sensitivity for the cross-section of interacting of the waves with the magnetic bundles to detect this. And I'm happy to come back to this and try to arrange this, understand this. So cooling is essential to sunspot stability. How can this be done? By downwards waves, or by, accordingly to Parker, sending alpha waves up into the atmosphere through the coupling of magneto waves. This has been studied, and I would just like to mention the work of my colleague Paul Kelly, who is looking at the acoustic wave propagation when fast acoustic waves interact with a magnetic field from different attack angles. So on first image here shows how the acoustic waves travel along the magnetic field lines, and you could see how the magnetic, the conversion of the wave mode conversion happens with waves going up as alpha waves. So they travel up and they can take the energy from these pockets, of gas, and then fast waves return back to the surface. Or we can have the other configuration where the fast wave, the acoustic waves, interacts more or less perpendicular to the magnetic field, and the conversion happens differently, where we have mainly the alpha waves returning back to the solar surface later, and then they convert again into slow waves. So this is known, it's been studied. If we want to, at one stage, to worry about how alpha waves and mode conversions can cool sunspots, then we can do this. All right. So whatever have we learned so far about analyzing this giant sunspot? That first thing we discovered, it's just my first conclusion because I can, I have a second part. We discovered species, we call them species of compact physical anomalies in the structure of strong magnetic regions. They are everywhere. They are conspicuously detected by helioseismology, and we call them strong scatterers of acoustic waves in the PMO spectrum. They are not visible in continuum intensity images, and we don't see them in the maps of the magnetic flux. They have this affinity with the umbral-penumbral boundary, and I don't know why. I've seen some papers, 2 papers, and if I have time, I'll mention them, about how many interesting things happen at the umbral-penumbral boundary. But this doesn't necessarily mean that we can just spatially correlate things. What's important for us, for my method, as Charlie and I, we decided to say is that helioseismic holography supports Parker's model of shallow fragmentation of magnetic fluxes, because we've seen these well-defined scatterers, and they are omnipresent. And helioseismic holography and other diagnostics find no evidence for oscillations or attendant waves sufficient to cause sunspot. So these waves that go down, or alpha waves is not part of this. We just discovered that structure, that it exists there, and it's permanent. I will leave this for discussion points, and sorry for being so much writing. The key words here is to understand why we have this affinity to the umbral-penumbral boundary. And then the other thing is, I would like to learn about umbral dots, and if there is a strong connection between acoustic scatterers and umbral dots. Because we can't rule out that must be a connection between them here. Right, so. And this is, I had a chat yesterday with Matthias about this structure, and then I zoomed in the internet and looked everywhere. And I don't know if that's the right paper, Matthias, but what I'm seeing here is a temporal evolution of subsurface magnetic field strength, that's Z, so depth -11, -3, and 0 megameters. And I can see these fragmentations, which is kind of, why not? Parker's model, maybe. So I would like to learn about this in terms of evolution and how they evolved as a discussion point. The next step was after the paper was published, okay, let's discover more of these. So we looked quickly at 2 other active regions, just to show you how they exist and how they behave in different structures. This is a sunspot of about 50 megameters, so smaller than the other one. And we do see scatterers, but one of them is actually in the penumbra, not necessarily at the boundary between umbra and penumbra. Fine. We generated maps, we look at them. Then we looked at a mini sunspot, or let's say Charlie defines this as being a pore, but it has a bit of a penumbra. And it has, as you could see, a massive acoustic scatterer. And it lasts. And the question is, thinking at Parker's model with, fragmentation of the magnetic flux, now I have this stable, long-lasting acoustic scatterer. We can see it in the other, the next 24 hours. Don't forget, all these images that I'm showing you are integrated over 24 hours to just identify from the statistic point of view well the location of these bits. We do see some phase shifts, probably more of, a chain of acoustic scatterers in the lower satellite sunspot. At the edge between umbra and penumbra, and it's interesting. We'll see what happens there. So again, we've noticed that these acoustic scatterers, they don't have any electromagnetic counterparts, and they are invisible in the magnetic maps of any kind. My question here, it's for a trigger discussion, is what is the function of these acoustic scatterers in evolution of an active region? And we're now looking at freshly emerging sunspots or regions to see if we detect these scatterers.
Can I ask you a question? For the continuum images that you put there, are those also averaged over 24 hours?
Not for-
When are those taken relative to the time?
Yeah, so this map is somewhere in the mid,
It's in the middle.
12 plus 12
Okay.
to be sure. Yeah.
Okay, thanks.
I think, Katie, that number develops during the 24-hour period over
Right.
which that was, over which the acoustic map was integrated. And and you see that the acoustic feature is elongated. And so that suggests that it was actually moving while the integration was. Don't really know.
That's what we call Duval's sunspot. It's been analyzed. Everyone knows it. And we've seen beautiful acoustic scatters. I'm advertising them as if they are big, right? Beautiful acoustic scatters, perfectly located around the Umbra Penumbra region. All right. Next step.
Can I have a question?
Yes.
So all the scatter, is in the sense, the phase shift in the sense that they are faster sound wave speed inside. Is that the sense of the phase shift, the sign of the phase shift? Is that effectively saying that these darker things are faster waves?
Mhm.
Is it-
Yeah, they have, what is it? 30 seconds they move. So when they go in, then they are quickly reflected, and it's a delay of 30 seconds.
So it's like a faster effective, the phase shift is in the sense of faster speed. Okay.
We think.
Huh?
We think.
Your acoustic anomaly things are larger than the umbra, and maybe are they the same size as the penumbra or a little bit smaller?
The anomalies.
Yeah, the
They-
anomaly on the left compared to the
Yeah.
continuum intensity on the right.
1, 2, 3.
No, I'm talking about the whole set of them.
Oh, the
There's sort of a, yeah, there's a.
Oh, this edge here. Yeah, I should have. Yeah, I put. Yeah, it's here. So that's the umbra, the penumbra quiet sun edges somewhere here.
They extend outside of the umbra, but
Some of them.
but not outside of the inner penumbra. They get into the inner penumbra.
Well, I mean, it just that it looked larger than the penumbra to me, so I was wondering.
I think they're not larger than the penumbra, but we can check that.
Another active region, because now my question was, I'm going to choose one that has some very good analysis online so that I don't discover everything from scratch about this. And I stopped at Stangalini's Sunspot. And this is a Nature paper. We reproduced everything in this paper, but I like the graphic, and they actually did a Helmholtz ordinary differential equation calculation for the modes of oscillation here. And we are able to reproduce this. Frankly, the fact that I see here the eigenvalues as they are in the map, I don't think I can speculate at the moment that there is a connection between this kind of oscillations inside the umbra and the existence of acoustic scatterers. But I want to highlight that people have looked at this, and mainly they've noticed the high frequency oscillation inside the umbra. And this is, right, this is the umbra penumbra boundary. And inside the umbra, you see all these high frequency oscillations that while outside we see normal, the 3.5 millihertz here with enough power. So it's a special sunspot because it displays the high frequency oscillations in the umbra. And immediately we thought, okay, is there a connection with the acoustic scatterers? The message here from their paper is that waves propagate through the sunspot and they go up. And as they do this, they travel upwards. Then what is this telling about the structure? So yeah, here is mainly our exercises because we have students interested in numerical simulations of this kind at Monash University. And we looked at all these 90 modes of oscillation with different plasmas. The challenge was to find the right parameters, like temperature of the sunspot, because the data from the sunspots from HMI were corrupted. You know, a big sunspot doesn't give us good reading for magnetic maps, intensity continuum. So we invoked a bit of, Hinode data. We're having here the plasma beta 1 structure, and then the sound speed, and then the lower map here is the alpha speed. All you see here is inside the umbra. So we try numerically to squeeze as much information as we can about the inner properties of umbra of this active region 1, 2, 5, 4, 6. Right, back to holography. We looked at properties of this active region. 3.5 millihertz can see all these absorptions of acoustic waves. Seismic emission gives us beautiful acoustic halos developed at 6 millihertz, and we can do a lot of statistics now in terms of evolution. What's interesting is that the acoustic halo shows anisotropy, and what you see as bright pixels there, it may be some local, we call them acoustic glories, but we need statistics here. We've done this in the past. I didn't want to reproduce this, but you see how the enhancement of the emission, so this time is not just local oscillations up and down of the photosphere. This is local emission. We have localized seismic, tiny seismic sources at 6 millihertz, mainly preferably between, the big sunspot and whatever is the trailing posed area here. Of course, questions about the acoustic evolution of the halo are coming in. And this is a profile of Hinode magnetic monolith, let's say, of this sunspot. And here is the phase map of this active region as it crosses the disk, right? 18th of July is left somewhere to the left, and 20th of July is, when the sunspot goes through the meridian. And yes, acoustic scatters are here, but I couldn't find one because these are maps integrated over 24 hours. They don't keep the same location, so they move, they restructure. We're in the process of analyzing actually what's the true lifetime of an acoustic scatterer, because if we divide our cubes to analyze, to get maps like this for, let's say, every 2 hours, then we have a problem with the signal to noise ratio, and we need to assess the correlation between ingression and egression measurements in holography differently. But it shows that even if, let's say, in the next 24 hours, the major structure of the sunspot is there, inside the umbra-penumbra edge, things change. So I'm thinking these magnetic bundles, if they are there, always highly dynamical, they can restructure. How can we see that? What's the flows? What are the flows of the plasma that allows this? Or maybe it's just the cooling system, right? When we have these oscillations of the plumps of the, how do you call this, hot gas things going up and down. And when it's going up, maybe we see some thermal signatures here. When it's going down, the magnetic bundles reshuffle. And I would like to learn more about this. Now, because I would like to allow time for questions, I found 2 papers about this sunspot, not too many. One, so this is iris observations by Bishop and Tripathi and Jelinek. And they identified presence of shocks affecting the profile of these lines. So we have silicon-4, carbon-2, magnesium-2K, and the slit was just, going through one of these edges, boundaries between umbra and penumbra. And they say that they measure 71 shocks in 97 minutes. Okay. I need an iris specialist to help me here.
1.5 minutes.
Oh, but along the slit? I mean, they could measure at different locations.
Yeah,
Yeah.
is it in the
Yeah.
same location or?
This could be 3 minutes.
Yeah, this,
This one was in the same location from what it
yeah,
said.
but you have many pixels long.
Yeah.
split, right?
Yeah. Would be nice to spatially locate all of this and temporally to see if the acoustic scatters are connected to this. I doubt, because then this is still high chromosphere, and the chromosphere is dense, and we have the same problem as with sunspots, and how much the transient, these shocks can travel deep down to the photospheric level.
Alina, is the Doppler profile integrated over the entire line, including the quiet sun, or is it just,
No.
Oh,
or is it just, I see two horizontal segments?
yeah, those are just.
It's just integrated.
I-
in the overall.
I think they read it at those locations. Yeah, this is exactly the. Okay. And these are the way they looked at AI 171 and the iris, but this is top chromosphere, right? And above, and they've noticed the shocks. I don't know if there is, as I said, any connection, but I'm open to understand the correlation between these curves and the location of the acoustic scatterers. But
Why do you need that?
we know what happens because this is the stability of a sunspot doesn't necessarily mean to look at photosphere and beneath. We can still look at what happens to the fill lines and how can they distribute in the fan structure. If we are not going too high, because if it's too high, probably that's not relevant.
How, I don't know this paper well, but I mean, were they watching for many hours in Iris and the shot
I
in the
should-
same
Let
location?
me see if
I think you have a plot in time there. It's 97 minutes. Right?
Yeah.
That's what it is. 97.
It's just, I think things evolve can evolve very quickly. And the location, you're seeing that the location of the acoustic scatters is moving.
Yeah.
That's.
It may not be
That's
connected.
challenging. Yeah.
And when we split the temporal analysis of the acoustic scatterers, I couldn't see, but we need to do a bit more work with the statistics. We couldn't see the same thing lasting for like 6 hours continuously.
The velocities are subsonic, though. They're less than
Yeah.
the speed of sound in the photosphere. About Mach 1/2,
Which velocities?
the Doppler velocities, right?
Yeah.
Here.
They're like maybe 5 plus or minus 4 or 5 kilometers.
And the last bit, if I may, is another paper that Stangalin, the same guys who published the Nature paper on this, they found circular polarization. I'm learning about this, but they still look at the same sunspot and at all these frequencies of downward propagating circular polarization disturbances. This is the whole literature thing that I could find about the sunspot, this magic sunspot. If we can connect it somehow, and if I can learn about this propagating spectropolarimetric disturbances, just saying that people are interested in this. So to conclude, and I'm quoting Charlie, what our seismic diagnostics now show is that the seamless magnetic monolith that has for centuries been what we see of sunspots, dark ombre, is breached, fragmented, full of holes, just barely beneath the deepest layers down, and to which our conventional telescopes can see. Maybe you can. So I'm hoping for understanding more and collaborating with colleagues. Thank you very much.
Thank you. Questions? Ragnar?
So
Yes.
for acoustically following these bundles, I mean, you're saying that they change from day to day. Sorry. Yeah. So what about instead have a sliding window?
Yeah.
So that you can find out if they're just moving around rather than appearing and disappearing.
Remember your moving sunspot, Lena?
Yeah,
Yes.
I didn't show that. We have a moving sunspot,
Uh-huh.
fast moving sunspot. But we had to do some tricks to check. Well, how do we do that to change to recenter
Yeah.
all the image to common
We can
reference
track,
point?
we can track the sunspot
We
or
track.
not.
Yeah.
And in one instance, sunspot moves through the
That's a fast moving sunspot.
if you like, the acoustic camera signature, and and you can see whether a given strong acoustic scatterer gets smeared or not, and it doesn't. It doesn't get smeared. It only lasts for hours, not nearly 24 hours.
They follow the sunspot. They are inside. Right?
Yeah.
Yes.
See, you're
So-
talking about the little peaks in the phase anomalies,
Yes.
Yeah, the little dark things.
and
Does it-
those little dots.
Those
Yeah.
little-
And you're saying that in the course of several hours, they change.
Yes, they change in just hours, in much less than a day.
But they're not smeared in one direction
No.
that suggests that
No.
they're moving.
Well, the reason to think that they last only hours is because the signature is not smeared when you don't track the motion of the sunspot. And so then the dots are, permuted. Some, occur earlier than others, but they're not smeared. They're still sharp.
Yeah.
So the sunspot is moving. The dot must have popped up and disappeared before it gets moved further. And then when you compare the pattern of dots where you track the sunspot and the pattern of where you didn't, the earlier ones are, appear further down the track and the later ones appear further up. So that's the kind of diagnostic that's been done, and we can do a much better job than that. But
How deep are these? What's the depth where you think this is representative?
within a megameter, that's that's by defocusing. Go ahead, Alina. I'm trying.
So this is a surface, and then the next one here where we can see a bit, it's 1.4 megameters, just that. After this is almost nothing, it's near noise here, plus. So they are not that deep.
So if you look at
So the dark line is right at the surface?
Yeah.
Yeah.
Which means it's this profile here,
Okay.
strong profile.
see this,
The next one is 1.4.
So as you go deeper, you don't see the anomalies.
yeah, it gets fuzzy. All those dots get fuzzy, and that means they're out of focus. So they must be shallow.
So what I don't understand is you're seeing the surface and slightly less than a megameter below the surface. And the magnetograms can measure the magnetic field of the surface. They see a fairly uniform field, and yet you're seeing something that's very ununiform.
Just barely beneath it.
And
But it
how
could
do you
be,
understand that?
it
Or
could,
don't you?
There's enough signal in the umbra actually that you can tell if there's magnetic structure inside.
Yes.
Yes. Okay.
Yeah, there is, yeah.
But
Okay. Good.
That is that.
those funnels seem to be more finely structured further down, right? Right. So why would you see them? It's homogeneous at the surface is what your cartoon showed, and it gets more structured farther down, but
Show your image of the poppies, the California poppies, the orange shrubs.
California box.
That was-
See that because you see how thin they are, if the wave comes and it's not going to see that.
So I have that was actually related to my comments or question. It perplexes me that you can't see any evidence of these scatterers, neither in the magnetic field nor in intensity and so on. Maybe if you use we have one other diagnostics that can measure a little deeper, which is the 1.5 micron lines, right?
Oh, yeah.
Maybe you could find something different.
Yes.
It's that line, the Big Bear magnetograms.
That's a good idea.
Big Bear has suspended gravity.
Yeah.
Right, but I think Big Bear does it more regularly.
Uh-huh. And you wouldn't,
You're a little below because you're using the iron lines and say mid atmosphere 200 kilometers, something like that. Those infrared lines are a little below what we call zero
So was that 1.5?
microns. Yeah.
now it's possible that the molecules in the sunspot may make the depth of it of the opaque depth shallower than it would be in the quiet sun. But why not
Sure.
look? Just why
But
not?
still the delta is the same, or similar, between these two
Right.
iron diagnostic. Might be worth a try.
So what is the cadence and the length of the observations that you need to actually determine this?
We've
How long
done
good time?
24 hours, but it's 24 hours. So we
Judging
can,
by the hour, you must not have a very long time sequence.
24-hour
Oh,
time series
yeah.
at moderate high
She
definition.
actually has looked at some
Maybe the
programs
high-
we did it.
sequences, but
But you could look for structure,
those do you
Do you have higher sequence resonate mine velocity and
but you could look for differing structure in the magnetic field.
Yeah.
This would suggest the magnetic field is more finely structured in the 1.5 micron than you would see with at a 6302 or 6173, right?
so just do a magnetic math.
Yeah.
Those exist, I'm pretty sure.
Well, if some of the also then going to the higher, slightly higher. I mean, just again, it's like, don't expect it to necessarily stop right at somebody's tau level. I mean, so you could also do the calcium.
The magnetic fields kind of merge, then it's more monolithic, right?
But to confirm it, that's what I'm saying is like, because like once you get a light bridge, they do start to show the differences at even. So it's again, it's putting the pieces together, right? Yeah.
No, but I mean, in general, the magnetic field of a sunspot in calcium is way more monolithic than in the photosphere.
Sure.
There's no structure.
Yeah.
you want to,
It's waiting there.
Can you estimate based on the scatter amplitude, how much perturbation to the wave speed you need to produce a scattering of that amplitude? Kind of just the wave propagation modeling through some inhomogeneous structure. How much wave speed perturbation do we need to produce this?
we can do that and haven't. But
Can simulate.
But you can almost do that on the back of an envelope, because the idea would be that the difference in temperature could be practically the temperature itself. 10,000 to 3,000, between 10,000 degrees and 3,000 degrees. If you just go down a scale height, which would be a few more kilometers. And so, that difference would be a significant fraction of pi, plus or minus pi.
Yeah, but I wonder is if you really do a forward model of wave propagation, do you get some signal of this amplitude if you do this kind of
Right.
to make a connection between the inhomogeneity you need and the scatter amplitude you get.
Right.
Understand this better.
Yes. So we haven't done that, or at least I haven't. And
Because the thing is, you expect the largest homogeneity, I would say, near the surface, but there or other observations don't see it, right? So
Yeah, yeah. See, this has to be something that happens in a very shallow layer. And in other words, you're looking, we can't see anything beneath about a megameter, or at least, at least it seems that holography is insensitive to anything that's less than 1 or 2 megameters deep. It just doesn't, the magnetic field is there, but it becomes transparent. So there has to be something radical happening between about a megameter and the surface where you see just, where you don't see these features. Right.
Is that just confinement of magnetic fields by the plasma, and that you have a plasma gradient, so that a density gradient, so that when you get closer to the atmosphere, you have spreading out
Yeah,
of the magnetic bundles?
right. Maybe, maybe. And also, let me come back to that. Also, we don't know that the magnetic flux is only 3,000 degrees. That's true at the surface, but we don't know what it is 100, kilometers beneath the surface. And then, yeah, the answer to your question, I don't think we know that yet. I think
So if the scale is too small, you wouldn't see any scattering, because the wavelengths of the waves.
That's right. We wouldn't.
So you have the two things working oppositely.
Yeah, it does.
Combines the signal.
It does help that what we're looking at is a couple of, several megameters across, and we would have a hard time resolving less than that.
Yeah.
In the P mode.
Yeah.
Band. That's right. Like
What is
5 megameters across.
megameters is your resolution, your spatial resolution in the acoustic?
Something like that.
Yeah. It's 5 to 6.
So my question would be going a little bit the picture that using sound waves might be U-boat. And could it be that your true resolution of these fibers is very broad, and that sometimes you have an interference pattern where you get a strong signal. See what I?
Yeah. Well, I might be missing your meaning now. What we see, for example, in a sunspot, we think, or that is where we see something local, that's an anomaly, and what we basically see are anomalies. If it were uniform, it wouldn't come across as a scatterer. It would, waves would come up, reflect specularly from it, and then that would be like, it would look like the quiet sun, except phase shifted, but otherwise boring, right? Now in the quiet sun, you could say that, the quiet sun is certainly a strong reflector, but we don't call it a scatterer simply because it's not, because it's,
Flat.
uniform and not anomalous. And so the scattering phenomenon is a result of certain things being different than something else in a very localized area.
But you don't see the interference in phase shifts.
No.
You only see interference in amplitude. And so it's basically a inversion of the interference that gives you the phase shift. So the phase shift should be the true locations of the perturbables.
Yeah, phase shifts are due to propagating through the region from species of different magnetic fields, presumably.
And even the signature between the scatterers is about a radian greater than the quiet zone.
So I'm a little confused about the topology here, right? The topology, you have these strong bundles of vertical field that below. Something happens in this magic megameter and we have strong vertical field space being here above. So you have sort of, I mean, it goes back to like the old wine glass, but there must be some transverse field component, strong transverse field in that layer where it's transitioning from a concentrated bundle to a space filling. So do we see transverse fields in the sunspot in these?
Horizontal. I mean, you're talking like parallel to the surface.
Parallel to the surface, some kind of, there would have to be a signal of this if there's
the
strong.
surface. The area is below the surface somewhere, right?
Right.
So you don't see it. Well, definitely not at the surface.
The problem is,
Yes, definitely not. So I mean,
the problem is,
magic layer. Yeah, I don't
you
know.
can,
Maybe you're talking about like in
The
the
umbra.
in the umbra.
In the umbra.
But the magic, it sounds like magic is happening or something in magic is happening at that penumbral transition. And that is a hot mess.
Well, the umbra, penumbra, but in the umbra too, these
Yeah, but
lilies are here.
you're seeing were accumulated at that umbral penumbral boundary and
Oh,
how that forms and what that actually is, because it's, this whole combination of structures and flows, right? That, I don't know how deep those influence, but they are, it's.
you always have to, it seems that there has to be transverse fields where you can't see them. And it's possible though that you can see them. It's
It's worried when you put crazy things, but where you can't see them.
although maybe you
Yeah.
could see them in a 1.5 mile.
Well, where that would be maybe, yeah.
Counted it, but you can try.
But what do the simulations say, Bob?
Well, remember, my simulation has a spot forming from the various pores coming together.
Mhm.
So, yes, we do see that there is some structure in the subsurface magnetic field because of that. I don't know that I quite agree with the model, but certainly you're going to see some subsurface. What I find difficult to understand is this sort of random changing in what you see in the shifts.
The
because
dynamics. Yeah.
it certainly changes with time. I mean, these things are rotating and they're moving around some and on a time scale of hours, but it's not a random thing. It's a much more organized thing. And so that's what I'm wondering about. Not that you're seeing substructure, since if they form from, as we observe, many sunspots really do form from merging smaller structures. Yeah, I expect substructure.
But then the question is, if you put together so many pores to get a sunspot, what happens in between with the gas, in between the magnetic structures of the pore?
And on what time scale?
Yeah. Yes.
Yeah.
I mean,
Where does it go?
geological surface is fast, but these things tend to be rooted fairly deep down where the time scale is slow. So, they come together over a period of, this was a few hours.
Right. I mean, that's what we see in observations too.
Yeah.
I mean, there's a range of timescales, but.
I don't know too much about, I've just started reading about the fluid instabilities of would they somehow reflect and create more instability inside to make this bundle like push them into, what do you think about?
I mean, main thing I have always been seeing in my simulation is that it's very difficult to hide something like this from not being visible at the surface. Sooner or later it breaks through. And I have tried hard. I totally failed to produce a sunspot like this. They always fall apart. That doesn't mean they don't exist, but
That's the problem.
That's actually really interesting.
Yeah.
Well, what you have to do to keep them from falling apart.
kilometers grid spacing.
But maybe we should send stuff downwards to cool it down.
What you have to do to
Go on.
keep them from falling apart is to get rid of the heat, you know, in the shallow.
Is when you have these intrusions, there always are channels where you get high entropy plasma back in there, and that wants to rise to the surface.
Yeah,
Essentially, this rises up. You start forming umbral dots that become bigger. They form a light, but sometimes they just form an island of granulation showing up in the center of the umbra. That's happening when you.
In the model that you did with Johan's dynamo info, there, as long as new flux was coming up from the underlying field, things said, yeah, it started to decay after you started having new flux coming up, right?
I mean, we didn't run that for long enough to really have a decay. I mean, that was mostly still in the formation phase of this activation, since we ran it for about 50 hours.
Go ahead.
So all these scatter, it's basically a wave speed, effective wave speed variation within this umbra, producing these scattering signals, right? So the effective wave speed is the plasma speed versus the sound. It's not the sound speed change. It's probably because magnetic field strength is varying. Would that be enough? Just in the umbra, there's local variation of field strength. So plasma speed is effectively changing to produce this kind of a.
You know, we've talked like that ourselves, but it's a bit of a swindle because the actual interaction, you know, could slow the wave or do various other things. You know, it's more complicated. We've talked about it as if it's an acoustic Wilson depression.
Right.
It just depresses the photosphere, but that's a lie, you know. But it works kind of nicely for various
Yeah,
purposes.
I mean, we did these wave sunspot with scanning using Hankel analysis. We only get one number for the sunspot outgoing wave
Right.
phase shift.
Yeah.
It was just assuming that the sunspot is of a higher phase speed, but it's a one number. We only were able to get one number out.
Right.
It's one sunspot. But you seem to get such a high resolution. You get these inhomogeneous.
You know, things like, for example,
Them. That's just incredible.
for example, we know that that the penumbra behaves differently from the umbra magnetically, you know, and that probably has to do with the tilt. And so you can't just say that it's the speed of sound changes. It's you know.
So I'm not saying, I'm saying the wave speed, that the fast mode speed effectively.
Yeah. Have you seen something like this in a naked sunspot? Kind of
Well, that's what,
answer the question whether the penumbra plays a role or not.
oh, you mean without a,
Yeah, a sunspot without penumbra.
this is getting a stable pore, a pore to be without a penumbra, to stay that way without either disappearing or running from a penumbra is tough.
Yeah,
I don't know how often that actually happens. It's pretty rare.
you know, we use the pore as a control because
Well,
that's the only place where
but that pore,
the scatterer is visible.
are you talking about that pore on the right?
The upper, you know, where the red.
I mean,
Yeah,
is it
but I,
or
but
even
there's
resolved?
pore there.
Is it just one number you get?
Then you've got then your magnetic field and all the flows and your evershed and everything just changes.
Nevertheless, Katie, that's the place where the scatterer becomes visible. It can't be anywhere else because there's just not room in the sunspot, you know.
Well, that's what I'm saying is a naked, what Matthias was saying, like a naked, or where you have pore, meaning Meaning I have a disturbance in the continuum, but I do not have a penumbra.
Yeah.
And you're trying to be very careful with definition.
Or like this, give it to me and then I'll get it in 4 hours.
That is that.
Yeah.
So, and that is that. There's
Yeah.
a penumbra.
Couple down here. There is a phase shift. Yeah, I agree down there.
Yeah, but
Right.
that is
So,
because of
so
the
that's
magnetic.
kind of a control.
The
Otherwise,
point is that you can.
otherwise,
Partial structuring
how carefully you were about
variations.
the acoustic optics, you wouldn't believe it. You know, you wouldn't
It's
believe it would be an artifact.
Right. And you have to be a little careful about like, again, penumbra and penumbra, because sometimes you can get these very small pieces of penumbra. And as soon as you get that, again, the whole dynamics has changed. You know?
Right.
So,
If you don't mind, I want to go back to the heat management thing.
Once the
because-
cover forms real, dynamic changes a lot.
at least the photosphere kind of in the case there.
The heat disposal problem, we, have tried to find evidence of somehow this being done by waves. We don't think that's possible. But here's the problem as we understand it. Whatever problems you have keeping the heat from getting up and getting, and getting out, it seems that is actually nevertheless what gets suppressed, because when they launched Solar Maximum mission, 1975, this was after Parker had posed his model of heat disposal. And that made us realize that the sunspot actually does eat that heat and keep it down for weeks. Okay, it just doesn't get out because the sunspot reduces not just the luminosity of the sun in a bright ring around it, it comes out nowhere. That energy is, somehow stuffed somewhere else.
I mean, the convection zone has a Kelvin-Helmholtz timescale of 100,000 years. I don't think there is really a problem at all. You can keep it there and it comes out later.
Yeah, because you somehow just have to stuff it low enough that the heat capacity of the gas is enough to accommodate.
So to make one of these seismic maps, how long a time series do you use?
24 hours.
24 hours.
And we are trying now to cut it down to, we did try 2 hours, but the signal to noise ratio is
So for six.
the correlation.
So for six, maybe.
We'll go for 6. Yeah.
And have a running window and see if that gives you more idea of what's happening, what the time.
Running window.
So
meaning
24
overlap.
is offset. You do 24 hours.
Yeah,
No.
not consecutive.
Not consecutive. So
But
I mean,
running.
you have 24.
With a bit of overlap.
Yeah.
But then you shift by 6 hours.
Oh, okay, yeah.
You're not going to get independent information,
Yeah.
but you could get an indication of which
Yeah.
pieces are changing and which aren't.
Yeah.
So it's kind of you got to be careful about the information onto it, but you could.
And
Now I have forgotten how big the difference between the rotation sunspot and the rotation that as it is determined out of the surrounding plasma is. There is a difference because the sunspots keep coming up and there is a drift because the source underneath is clean. So my question is, are you keeping targets? Or is part of what you observe this component?
So they follow the sunspot. They don't stay behind. It's just very localized.
Yeah, but the sunspot itself moves within the plasma. That's
Yeah.
why.
It moves.
Maybe nothing.
Yeah. We have this fast moving sunspot, and everything is just following, including even the acoustic halo is just following the
Moves.
sunspot.
It's a sunspot.
And we did some tricks with looking at ahead of the direction where the sunspot was moving to sense any kind of flows, anything. It's as if the quiet sun doesn't even know that the monster sunspot is coming into that direction with its own acoustic scatterers. The quiet sun doesn't know about this. I would have published a Nature paper if the quiet sun would know about the monster coming.
But you're talking about sunspots moving because it's actually a flux bundle that's inclined and you're just seeing it. Yeah. So that should show up as horizontal field in the sunspot, right? It wouldn't be vertical then at the surface.
Yeah, you see, as they move to the limb, you're seeing the line of sight becomes more horizontal.
Yeah, of course. But I'm talking about if you have a flux bundle that's still rising, and that is, so this is the photosphere and this is the flux bundle. And as it rises, if it's not vertical, it will move the sunspot. And that's what you're talking about, right?
Yes.
Yeah,
See,
or twist.
this king and is moving upward. And when it comes close to the surface, then it zips vertical. So, and in this way, it moves different from the plasma. It's
Yeah.
not, you won't see much of a horizontal component.
Okay.
And that's what your model, isn't it? Your model pretty quickly develops to a vertical magnetic field that's connected deep beneath the surface.
Yeah, but it's not I mean, haven't looked in detail, and we can do that while I'm still here. It's not completely uniform though, because what I found is that each of the pores are pretty uniform and down deep, but I don't yet know how long it is for the merger to become more uniform as they come together. I mean, you see at the surface, the light bridge only lasts for a fairly short time, for instance. But if I looked a bit later at log intensity, and you can see still some of the structures in there. It's something we have to look at. I don't know.
By the way, Elena noticed that, Elena Brock, who did this work, noticed that light bridges, very commonly, they're like a half dozen at least, that each one of them has a strong acoustic scatter in the middle of it.
Well, because, acoustic scatters are stronger, but I think what Michael was saying is clearly what you observe. So flux tube comes up, it gets filamented by the convection, and you see little things coming up, and they move to come over where the deeper roots of the flux tube were as stuff comes up. So that's why you see things spreading out to form the spot pairs.
Matthias, you're colliding sunspots. This was the suns in these cases, the motion of the sunspot, the shear motion, is caused only by fluid and not by the flux tube coming up and the sunspots expand.
It's magnetic tension in the end. I drag them at the bottom bounding 8 megameters beneath the surface. So you incline the field a little bit. You have tension forces which then drag the surface along. But there's no flux emergence. There is some, because when you have these sunspots colliding, you get some flux cancellation, some of this kind of boils back up after they pass each other.
Here's an elementary question. If you have two poles that are connected by a magnetic loop, then they are going to be attracted. They're going to experience an attractive force. But now suppose you have north-south here and south-north here. Will this south and north feel an attraction? Even in the magnetic fields are not, not connected. In other words, they don't connect each other. Or a repulse.
No, didn't somebody estimate that how much the sunspots should attract each other? It was related to this question with thin flux tubes rising. And once they hit the surface, they should kind of move away much faster than they are. I think somebody estimated
Yeah,
how much.
it's only in the corona they know the current because the current is not shielded. In
Yeah.
theory, there's a return current. It's
Just
shielded.
they're shielded.
Yeah, they don't, they shouldn't feel the force. It's the force is through the corona. It's like two dipole, two charges sitting
Yeah,
there.
yeah.
And then they attract each other. It's basically that. But because they are, okay, that's a.
So now this is a case where there's a current sheet that separates them to keep the magnetic field, to keep this magnetic field from connecting, this pole from connecting to this pole. There's a current sheet. And what does that do to the mutual, attraction or repulsion?
Shoes. I mean, you're talking about a pseudo streamer kind of structure. Sorry.
Yeah.
Well,
Well, I'm wondering, if those magnetic poles repel each other, even though they're opposite side.
sorry.
So what did you mean by the fields being shielded deeper down?
In the deeper interior, there's a,
They have a ring current.
they have a current shielding.
Going
Yeah.
around.
Oh,
So the current, they don't feel each other. They don't have any.
This magnet, I mean, it's kind of like a coil, right? You have a ring current, inside the coil, nothing outside.
They don't.
so,
sense each other.
so magnetic fields are coaxial cables.
So the force is still the corona when they
Yeah, okay.
turns naked.
Which will make a signature in the photosphere. I'm thinking about the
So that's why-
decomposition and such. Yeah.
Yeah,
So
so they attract through the corona, in the corona.
Okay, it's 3:25. We can thank our speaker and we close this meeting.